Hello, in this video we are going to look at one problem from CSIR NET June 2018 Physical Science paper, booklet B, part B, problem number 21. So which is the first problem of part B. To my opinion, this problem is very interesting because some students might make some mistakes in this problem while in hurry in the exam hall. And to the end of the video, we'll describe what are the common mistakes people can make and how to avoid those mistakes. Now let us look at the problem itself. So here you see a second order differential equation is given with some boundary conditions. X at t equal to 0 is 0 and x at t equal to 1 is 1. We have to find the value for x, the function x at t equal to 2. So there are of course 4 options, and as we know only one option is correct from this. Now if we look at this problem carefully, we see that the differential equation is a second order differential equation and it is non-linear. We know some linear equations can be solved very easily, but as I said, this problem is interesting because this problem is also tricky. We have to find the trick and then we can solve it very easily. Now we see the given equation is d2x dt2 plus 1 by x dx dt square minus dx dt equal to 0, the given equation. As we see, the x is in the denominator, so as we generally do, we will multiply this equation by x, so we get this x d2x dt2 plus dx dt whole square minus x dx dt equal to 0. Now how to solve this equation? As we have already mentioned, this equation is not linear equation because it contains power of dx dt. Also, there are not many well-known methods to solve a general non-linear differential equation. But in this problem, for this equation, there is a trick. We can use the trick to basically transform the equation into a very easier one, which we can solve very easily. So here is the trick. We can write this equation as d dt of x dx dt equal to x dx dt, which is of the form dv dt equal to v, where v equal to x dx dt. Now this is very easy to solve dv dt equal to v. This is well known and very elementary. So if we solve it, we get v equal to a exponential t for some arbitrary constant a. So this can also be written as x dx dt equal to a exponential t because v was nothing but x dx dt, or equivalently we can write x dx equal to a exponential t dt. This upon integration can give us the function x itself. Now as boundary conditions are given at t equal to 0 and at t equal to 1, we will integrate first from t equal to 0 to t equal to 1. So corresponding x at t equal to 0 and x at t equal to 1 are given in the problem. We can check it. The value of x at t equal to 0 is 0 and the value of x at t equal to 1 is 1. Those are given already. And we put these values in this above equation. From that we get half minus 0 equal to a times e minus 1. That is by putting the upper limits minus putting the lower limit. So from this the value of a is clear, which is 1 by 2 times e minus 1. Now to find x at t equal to 2, we integrate on different limits from t equal to 0 to t equal to 2, and we get x square by 2 putting the correct limits, and on the right a exponential t, and from t equal to 0 to t equal to 2. Now we have to find x at t equal to 2, but x at t equal to 0 we know which is 0 actually, which is given. Now putting these limits, we get x at t equal to 2 square by 2 minus 0 is a times e square minus 1. Now we put the value for a, which is 1 by 2 e minus 1 and times e square minus 1. We get x at t equal to 2 to be square root of e plus 1, that option is given, and therefore this is the correct answer. But as we mentioned earlier, some possible errors can occur while solving this problem in the exam hall. So we will see where exactly they can occur. For that, we go to one of our previous slides where we found dv dt equal to v and solved the equation. So here is the slide. First the given equation, and then we multiplied this by x, the whole equation, and then we wrote that in a precise form, and then in terms of v, the equation was dv dt equal to v. Then we solved this and we got v equal to a exponential t. But here one might try to calculate the value of a using some boundary conditions, because some boundary conditions are given. So the question here is whether we can calculate the value of a using the given limits or using the boundary conditions. So for example, whether we can put t equal to 0 in the above equation to find the value of a. But for that we need to know v at t equal to 0. But as the value for v at t equal to 0 is not directly given, we calculate it to be v at t equal to 0 to be 0, as v equal to x dx dt, and x at t equal to 0 is 0. Now we put these values in the above equation and we get v at t equal to 0 to be equal to a e power 0, which of course implies a equal to 0. But did you see something serious here? So we are getting the value of a to be 0, but we had already calculated the value of a by some other means to be 1 by 2 times e minus 1, if you remember. So now this is actually a contradiction, as we are getting two different values for a by two different methods. So we made some mistake somewhere. And can you find where exactly we made this mistake? So we had done something wrong already, and here is what is wrong. The wrong thing is v at t equal to 0 is 0, as v equal to x dx dt. This is not making any sense now, because x at t equal to 0 is 0 does not imply v at t equal to 0 must be 0, as dx dt at t equal to 0 could be infinity, might not exist at all. So we cannot calculate v at t equal to 0 from this equation by just putting x at t equal to 0. So x here is a function which is 0 at t equal to 0 but is not differentiable at t equal to 0. Now can you guess what type of functions they are? Here we see one such. If we look at the graph, we see that the graph is taking value 0 at t equal to 0, and the tangent line to the graph at t equal to 0, that is at the origin, is vertical, that is perpendicular to the t-axis. Since this tangent is vertical, the graph or the function is not differentiable at the origin. So finally we understand why we cannot put t equal to 0 to find the value of constant a in the previous slide. Thank you for watching this video, and please subscribe our channel for more videos and updates.